Hi, everyone. Thank you for joining our Designing Your Power Plant webinar today. Today, we will have Christian Mueller as our main presenter, who is the Jenbacher Senior Sales Manager. He will be followed by our General Manager of North America, Karsten Strick, who will navigate the question and answering. Please remember to enter questions as we go through the webinar via the question widget. Thank you. Enjoy today's webinar.
I'd like to welcome you to our webinar platform. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the Questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We will allocate some time at the end of the session to address any questions or comments you may have. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. Now, please allow me to share a short presentation about our company, followed by today's webinar. At INNIO, we are moving energy forward with a focus on innovative gas engines technology. We develop, manufacture, monitor, and service fuel-flexible engines for power generation and compression solutions. Our Jenbacher business is specialized in power generation. INNIO's Jenbacher North American Sales and Service Hub is headquartered in Houston, Texas, and we have operations in Wisconsin, USA, as well as in Ontario, Canada, with INNIO's global headquarters and our core innovation center based in Austria. Out of our more than 3,500 global employees, more than 500 highly qualified INNIO engineers are focused on innovation. INNIO's Jenbacher business has more than 2,000 employees around the world. The first Jenbacher gas engine was manufactured in 1957. In total, Jenbacher's success builds on more than 90 years of engine experience. So far, from about 25,000 engines for power generation and CHP delivered worldwide, around 1,100 have been delivered to customers in North America. Today, INNIO runs manufacturing facilities with a total of 65,000 square meters, producing 5 product lines of high-tech engines with outputs from 200 kilowatts to as high as 10 megawatts. Our engines are known for overall efficiencies of 90% and more, their durability, fast start capabilities, and the ability to run on a broad range of fuels, including hydrogen. Jenbacher also offers a comprehensive set of lifecycle services. Jenbacher has always been a frontrunner in the gas engine industry. In addition to a series of world's firsts in technology, the business also has a history of growth in the United States and Canada. What started with a small sales and service office in Boston 30 years ago has grown into a large network of expert INNIO and distributor sales and service, warehousing, and logistics teams across North America. Jenbacher engines meet our North American customers' needs with top reliability and performance, delivering total efficiencies of up to 95% in cogeneration mode. We offer established, field-tested designs, optimized, robust engine components, along with a proven monitoring and control concept. Our engines can run on natural gas as well as a broad variety of renewable or waste gases. This makes them a great solution for reducing our customers' CO2 footprint. With the capacity to run on hydrogen, the potential to save even more emissions in the future is becoming reality. Our service organization provides everything you need to profitably run your Jenbacher power plant. You choose your tailored level of support, and INNIO will deliver everything from the digital myPlant asset performance management solution for optimized uptime and reduced lifecycle costs, all the way to remote operation, as well as fast on-site service support from our team of technicians. We also run a remanufacturing program for efficient overhauls and provide you with comprehensive conversion, modification, and upgrade packages to help you make the most of your Jenbacher engine. Let's look at a few of the most interesting Jenbacher solutions for North America. Most Jenbacher power plants run in combined heat and power mode and use up to 40% less primary energy compared to conventional generation of heat and power. We offer innovative microgrid solutions for a stable 24/7 power and heat supply, even if cities face a blackout. With our innovative greenhouse solutions, we power and heat greenhouses and grow houses, while cleaning the exhaust gas for use as fertilizer, which promotes plant growth. Jenbacher-powered data center power plants deliver lower emissions along with fast start capability based on reliable pipeline fuel operation. Using renewable wastewater gas in Jenbacher engines can provide 100% of a sewage plant's energy needs and in the long run, achieve significant cost savings. We are ready for H2. Jenbacher's products are prepared for a CO2 neutral world and can support you with engines ready to run on hydrogen today. When you choose Jenbacher engines, you decide for a greener and more profitable future. INNIO, changing the world with better energy.
Thank you, everyone, and welcome to today's webinar. This is myself, Christian Mueller, Senior Sales Manager for Jenbacher, and I will guide you through this webinar here today. So, as we heard in the video, INNIO is a leading energy solutions and service provider empowering industries and communities around the globe, headquartered in Jenbach, Austria, where our Jenbacher engines are built, with also operations here in the US. We deliver sustainable, innovative solutions for power generation and have been helping industries and communities generate and manage energy efficiently and sustainable in a changing landscape. So, as we go today about this webinar, Designing Your Power Plant, a little background as we see the challenges that industries face today, especially also in the utility space. We all know that the energy transition is well on its way, which presents opportunities, but also challenges. The coal and nuclear baseload power plants are being phased out, in some places faster than in others, but generally that is a trend, and they're being replaced by expanding renewable power generation, which uses gas as a bridging technology. The volatility in the grid with all these renewable energy sources has led to lower grid stability, which requires then having flexible, dispatchable power and heat generation through gas engines as one means to help with that. And we also know that the infrastructure, to some extent, is aging, and there are different thoughts about how to potentially even use the gas infrastructure in place for future uses in hydrogen. And that's also a trend which we are addressing with our solutions. So now, as we get right into it, as mentioned in the video, we have a wide range of product options available, from the very small 208 engine, a couple hundred kW, up to the 10 megawatt J920. So in this presentation, I'm mainly going to focus on the larger engines, which would be the Jenbacher Type 6, from about 2 to 4.5 megawatts, and I'll also talk a little bit about the Type 9, as these would be really for power plant solutions, probably the preferred solution due to their high power density and high output. As we look at power generation solutions, one thing we have seen in the market is that there's a trend to a more modular concept, going away from very large power plants to a more flexible, possibly distributed energy generation concept, which would have smaller plants, be it 20 megawatts, 50 megawatts, and there our modular systems are really a perfect fit based on the Type 6, as we can offer a modular design in these containerized solutions, as you see there on their picture, which offer you the very high fuel efficiency you would expect from a utility grade power plant. Also the reliability, obviously with multiple engines. They have high ambient temperature and altitude capabilities depending on where your site is. They offer options for black start and rapid load response. The footprint is very compact due to the high power output of these engines, as well as reduced emissions with SCR catalysts and potentially future hydrogen use, backed really by decades of our experience with these platforms. So this is a new concept we are promoting in this market, are these modular, fully containerized power plant solutions, which are offered through us at Jenbacher. If we look at some of the advantages these modular systems offer, it's really the high flexibility and the short time to install these. So on average, you could expect these units to be delivered in around 12 months at site, which is much faster than a traditional power plant. They're very flexible in terms of their size. You could start off with one or two and expand as you grow. So obviously the concept allows for that growth. They have the inherent black start capability, very high efficiency, and due to the use of multiple engines, you have excellent part load capability, meaning you can turn on and off engines as needed and always run the engines which you are operating at very high load factors, meaning very high fuel efficiency. That's a major advantage versus a very large single shaft engine or turbine, which would in part load have not the optimum performance. The Type 6 platform is also highly developed in terms of the combustion technology. It has a dual turbocharging system, which allows improved flexibility and a larger operating range in terms of ambient capabilities. So these engines are often installed at higher elevations or higher temperatures. Routinely we have up to 5,000 feet or over 104 degrees. And through this turbocharger concept we have here, these can be adjusted to accommodate those higher elevations and higher temperatures and still produce the same nominal output. Conceivably for most installations in the US, you would expect that they could achieve their full output at site, which is obviously a great advantage compared to combustion turbines. We know black start and rapid load response are also important, and we offer a wide range of options there. So a typical gas engine would start more or less in 300 seconds or about 5 minutes right over here. But we understand that may not always be the time the customer wants. So we offer different fast start options, getting incrementally faster. So there's a sort of a typical fast start option, which would be around 3 minutes. And then we have options for starting in 90 seconds and 45 seconds to full load. So really we can cater to anything from a very rapid start and very rapid load acceptance, if that's what's needed, to a more, let's say, gradual load acceptance. And we can cater our product to meet those requirements. We also know that grid code compliance is becoming more important as these units are used to support the grid. So there's static grid support where a defined voltage and frequency range is set and the units will stay on the grid throughout that range. So there's also dynamic grid support, which is a fault ride-through capability and reactive current supply. And we also offer certifications for those. So we're seeing more and more of that in the requests we're handling as customers are asking for these type of solutions. Now going a little more in detail on those two engines I had mentioned, the 624 and also the 920. So these are the two options really for utility style power plants, which we're promoting. The 624 is the 4.5 megawatt unit, which I had just talked about a bit here. It is running on typically pipeline natural gas, and the performance data we have here is based on methane number 80. All gas engines are always rated at a certain methane number, but obviously we also have fuel flexibility to go with lower methane numbers. So this engine typically produces medium voltage power at 13.8. We also have other voltages as options. Start times anywhere between 3 and 5 minutes are sort of the standard. NOx emissions around 1.2 grams per mechanical kilowatt hour or 13 pounds per hour. But obviously we know that in many cases SCRs are needed, and that can be dropped down very substantially. We have SCR catalysts with 95 to 97% reductions available, which will then drop those emissions, those NOx emissions substantially. The heat rate is about 7,400 based on LHV. So obviously an excellent heat rate for this product. And this is a high-speed engine, a 1500 RPM with the gearbox design. The 920 is our largest engine on 60 hertz. It's rated at 9.3 megawatts. It's a medium-speed engine at 900 RPMs. Sort of similar characteristics like the 624 in terms of voltages, startup times. It does have, obviously, since it's a larger engine, a medium-speed engine, a bit of a higher efficiency, meaning a lower heat rate around 7,000 BTUs per kilowatt hour. And if I were to contrast these engines, the 920, obviously, due to its higher efficiency and higher power output, might be an engine to use for very large plants in the 100 megawatts type space. Also, those plants which would be base load, where you have advantages for using the higher efficiency engine. The J624 is a more flexible option for smaller plants, somewhere around 10 to 60, 70 megawatts, and also for peaking plants, because specifically these high-speed engines are on a per kW basis offer a lower cost than a medium-speed engine. So they have a very attractive capital cost associated with them, while still maintaining very good outputs and performances. So these would be very well suitable for let's say, smaller type peaking plants. Now, if we look at the modular solutions, and again, I'm going to focus a bit on the 624, the Type 6 platform. Jenbacher offers these containerized systems, which you see here. And we basically have two versions. One is the so-called 2-container design, and one is the 3-container design. So for the larger 624 engines, they all come in this 3-container design, which is a fully prepackaged system for the engine generator set, with all the necessary auxiliary systems, cooling systems, ventilation, electrical controls, hydraulics, and so forth. And it's fully packaged by us at our factory. So if we look at a picture of how a plant like this looks like, this is, for example, a typical 20 megawatt plant, where you see these containers lined up next to each other, and a very compact footprint, as you see here. And in essence, the power plant is almost complete if you look at what we supply. So we provide the containerized system, which includes the SCR, that's the little gray box there. Then really all that's needed at site is a silencer. Depending on the configuration, the silencer can be either located on the unit or next to it, behind it, with the stack there. And then you would have a centralized fluid storage system here, which would be for your urea and lube oil for the engines. And in the background would be your 13.8 medium voltage power distribution center, as well as the auxiliary low voltage distribution. Gas supply down here, and your step-up transformer up there. So in essence, a very compact power plant design, where you already have basically almost 80% assembled from our Jenbacher scope, and there's minimal site work needed. If we look at the container a little more in detail, if we do a cutaway, you can see the engine sits here at the bottom. It basically takes up the full length of the container, with the hydraulic skid sitting at the back. Up here on this, let's say, medium level is another containerized system which houses the air inlet ventilation, as well as here the gas supply train. And then on top of the roof sit the radiators, as well as the ventilation inlet. And you can see here in this concept, the stack and the silencer are actually located on the container. So that also helps to save a little bit of footprint, and that's definitely also possible. A cutaway from the top, again, shows the engine sitting here with the hydraulic skid to the side. It has a dedicated controls room, which is really nice. Operators love that. where we have our DAN controller there, and we have a junction box for the medium voltage connection right over here. The switch gear for these engines, since they're medium voltage, are typically external and not part of this container. As we now look at a division of responsibility, I already talked about it briefly on that photo there. So we, as a core base scope, offer the containers, including various options. Then there are a couple things which customers can select to be supplied by Jenbacher, which would be the medium voltage switchgear. We have done that. We can offer the exhaust stacks either on skid or off skid, together with an SCR. We can do a plant level control system, meaning a master control which controls the whole plant and takes a centralized signal from the customer telling how many engines are supposed to run at which power output. We can organize the transportation of these units to site, as well as the reassembly of these containers. Always part of our scope is the commissioning of the engines. That's just part of our base scope. So then what's left if a customer were to select all these things? It's really the site preparation, including the foundations, the gas and electric utility connections, the interconnect piping and cabling going to the containers, the urea and fluid storage system. We then work together with the customer on the engineering and project management. We help you design the whole system and the layout, and certainly also the project management, site management. We help with that. The only thing we would typically not do then in that case would be the site permits, as that's best done by someone local for the interconnect as well as the emissions. So this is just a typical division of responsibility which we would have. As we look at the reassembly of these units, just to give you some kind of an idea. So typically the first thing is you have a crane at the site, check the foundations, make sure they're level. It's really important to have good foundations there. Then we position the engine model, which is this A here, that contains the engine, which is really the heaviest one. And also the infrastructure model, which is the B, which has the controls and the hydraulics in it. Then we seal the containers, make sure we have that in place, put the ventilation system module on the top, and lastly, the radiators on the top, as well as the SCR systems. So in a typical kind of a power plant, as far as the time it takes to do that, it's about a month to get that all reassembled and tested. And the actual assembly is probably only about a week. But then, just to have everything complete, it's about a month to do that, which is really quick. And you could do multiple of these units in parallel. So that gives you kind of an idea of the work required at site to put this back together. This is a top-down view. There's different ways for multiple engines you can do it. You typically arrange them in these rows. You could have multiple rows there. In the center, you would have your power distribution center, and then to the top, you would have your transformers as well as the fluid storage. So what we typically do is we provide customers these typical layout drawings, which shows the total amount of space needed, the spacing between the containers. So we do that routinely for customers as they design their power plants. This is a typical single line of that power distribution center, which would be needed. So you have the generators here lined up next to each other. Then in the power distribution center, you would have your medium voltage 13.8 or 12.47 or whichever voltage it might be, breakers lined up there on a common bus. You would have one auxiliary breaker feeding a step-down transformer to 480 volt, which would feed the auxiliaries of the containers, which need 480 volt, the radiators and so forth. And then you would have your main connection, your tie breaker right over here. And we would have a master control system, which we offer, which would be able to parallel all these breakers, close the breakers, parallel the units to one another or to the utility. So we can accommodate, various designs of these type of power distribution systems. Now we understand that there are also some customers who might prefer a more typical stationary solution rather than a containerized system, and that might be especially the case for very large plants. And I want to show you based on the 920, for example, this is how it looks. I mean, this is a 4-unit installation, about 50 megawatts. So, very typical type utility scale power plants. which we have helped design as well, where you have the engines in a conventional powerhouse with the SCR stacks behind it, and then the radiator group here, and to the side you would have the electrical systems as well as the fluid storage. So this is a very typical. Probably most utilities who have been in the generation business know these type of power plants. So that's definitely something which can be done with the 920. However, it could also be done with the 624, and we have installed quite a few of these, especially in the UK, where you would have really a great number of these engines. Sometimes like 14 engines lined up right next to each other. Since these are high-speed engines, they don't require really any big support foundations or elevated platforms or ducted ventilation systems, which you might know from medium-speed engine installations. You can really just line them up right next to the other with a couple feet of space between them, which is then very compact. You get 60 megawatts here in a pretty compact space, and a relatively inexpensive building. You could put the radiators on the top or behind it, which was also commonly done to save some cost on the structure. But these type of building concepts, they do have their advantages as well compared to a medium speed plant, and you might actually discover that it has a lower cost than a typical medium speed plant, which has less engines obviously, but the whole building, the whole structure, everything is more expensive to accommodate these larger engines. Now, I also want to talk a little about the myPlant solution, as I think this is an important part of our capabilities for power plants. The myPlant asset performance management system is our digital solution, which helps make your operation more efficient, reduce your maintenance cost, and monitor emission regulation compliance, which we know is very important. So how does it work? We basically have our engines connected through the internet to our myPlant performance servers, which then allow you to access the data through your wireless device, your phone, your laptop, allows you to do real-time monitoring and performance analysis of the asset, and at the same time is connected to our 24/7 technical support, which is really important because it allows the technicians to monitor and support you with any questions or any issues you might have on the plant, as they can log in and in real time see all the assets, the performance of them. So what do we do to make your operation more efficient? We do the monitoring and reporting, so you have really fast access to the information. You have historical as well as live data and a centralized fleet view if you have multiple engines. You see the maintenance scheduling there, which tells you when maintenance might be due in future. And then really this consolidated easy access of all the engine data is what is there, and it alerts you with notifications to unplanned events, to maintenance events, to you can really set it up in whichever way you want to provide you these alerts on your phone. We also want to help lower the cost of maintenance. So basically, we try to avoid unplanned maintenance shutdowns. So what we do is we obviously continually monitor the systems, and if there's anything we notice that might be out of spec, which might in future lead to an unplanned outage, we can detect that and then fix it before it leads to an outage. And by doing that, we really reduce the on-site visits, because many of these things could also be solved remotely, or maybe we could assist the customer taking care of that, and it reduces the need for us to travel out, which helps you save costs and also return the unit to operation quicker. So it's really we work very closely with our customers through this online system to keep their engines up and running. Emission compliance. So emissions monitoring with continuous emission monitoring devices like a NOx sensor are something which are probably needed more and more as regulations increase around on-site emissions. So we offer these solutions, these NOx monitors, and then obviously you can check through myPlant that your engines are maintaining their emission compliance. And you might also set up notifications if your engines are, for example, starting to exceed certain limits or averages which they're not allowed to exceed. So it really allows you to continuously monitor and make sure that you're in compliance with the emissions for which the site is permitted. This myPlant technology has been very proven. We've expanded the functionality over the years, as I mentioned, quite a bit. We have about 12,000 digitally connected engines, about 4,000 active users which use this, and it has led to, on average, a 60+% remote fix rate, meaning we can avoid a lot of technicians going out there by having the system and doing a remote fix together with the customer on site. Now a little about a couple case studies I wanted to show you here, to show you our power plant solutions as they are working. One is, and you already saw that picture, is IMG Energy Solutions in Pennsylvania. So this is the Wolf Run project, and it's basically used to provide peak electricity generation during peak hours, and runs now actually approximately about 5,000 hours a year. It was less, but now it's running more as there are more peak hours and more economically advantageous hours to operate. These are our 4 megawatt or 4.2 megawatts, in this case was the rating here, 624 engines, delivering a total of 2.1 megawatts. And this customer specifically chose these containerized systems. They had some experience with a typical conventional power plant design of larger medium speed engines, which was not always very advantageous in terms of scheduling time to complete. There was overruns on the schedules, certain overruns on cost, and they then opted for these prepackaged solutions because it basically took the risk on the timing as well as on the cost out of this power plant. As the prepackaged solution comes, pre-engineered, it's ready to be reassembled, and it was really a solution which they then standardized on and have been installing quite a few of these sites. And initially they had gone with the traditional power plant, but now they're mainly using these containerized 624 solutions. Another site, which was also done with the help of IMG, is at Pittsburgh International Airport. It's a pretty cool site with also 5 of these containerized 624 units, again with about 20 megawatts. And this is really one of the first airports which decided to install a microgrid, which allows them to provide 100% of their power through these gas engines. So not only do they have the chance to run these in grid parallel as needed, but they can also go completely island mode. So if there's an outage, and obviously an airport can never have an outage in terms of power, they can start these units, they can black start and island the whole airport, which really provides a very resilient solution to this customer. And it's a testament to our engines as well, since they selected this technology to be that reliable source of energy in case the grid is not. And it's an awesome site there at that airport. Another one with the 920 now is right here in Texas, not too far from Houston. This is a 50 megawatt site, just a bit west of Houston on the way to San Antonio, where we have 6 of these J920 Flextra generator sets there installed at Sky Global. These units are designed for continuous operation, although they operate sort of in a peak to mid-merit type application, where originally they were probably intended to only run a couple hundred hours, but we've seen over the years that the run hours on these units have steadily increased year on year, and they have now, during the summertime, they're sometimes running almost continuously, providing power to ERCOT here, to the Texas grid. And they were really reliable during the winter storm Uri a couple of years back, when, as many of you probably know, there were widespread outages in terms of the electric grid and also the gas grid. They were able to run these units continuously during that week. They had a local reliable gas supply, and they were basically feeding 50 megawatts back into the grid during that time, which was helpful for the customers, and obviously also financially very attractive to the owners of this site, being able to operate at those, as we know, very high rate hours during that 1 week in in February. If we now go even one step larger, this is our largest plant with the 920s in Kiel. It shows you kind of a top-down view, and it's a pretty neat site. This is an old coal plant where they decided to install gas engines and replace the coal boilers. So if we look at this timeline, the old plant was a 300 megawatt sort of net output, like coal plant, about 295 heat output. So it's really like a combined CHP type application with about a 50% total efficiency. So the plant was very old, over 50 years old. It had a low number of starts and really was not, it could only support a low number of starts. You know, you can't start and stop a coal plant very frequently. And that just was not anymore what this customer needed in today's times. So they decided to take those old coal boilers out and put in 20 of our 920 engines, which produce a combined output of about 190 megawatts electric and 190 thermal, which is in total efficiency of over 90%. So they're using this heat of these engines in a district heating type applications for the local community. These engines are much more flexible in terms of start time. You know, they start up in 5 minutes, and you can ramp them up and down by basically anywhere from 4 megawatts, which would be 50% of a single engine, up to 190 megawatts, which would be full load on all 20 engines. So a very flexible operational profile is possible with these engines. And then just recently, we together with this customer announced that these engines will be converted to 100% hydrogen by 2035. We made that commitment together with the customer, which basically provides that path forward towards a carbon neutral time when hydrogen will be available and when they will want to run this on hydrogen. And the important message here is that these engines, which are today operating on natural gas, can be converted to 100% hydrogen in the future. And that's really our commitment across the whole product line. If I now go and show you the slide here on hydrogen, it shows again our engines from type 2, 3, 4, 6, and 9. Then all of these engines are what we call ready for H2. So they can accept as a standard low blends around 5%. And then with this optional ready for H2 package, up to 25% hydrogen blended into the natural gas without typically any derate. So full output. And that is a stepping stone towards the pure hydrogen scenario, case B, where there might be, you know, a mix of pipeline and hydrogen, pipeline natural gas and hydrogen, or C, just pure hydrogen. And as the first product on pure hydrogen, we launched the Type 4 about 2-3 years ago, and that is on pure hydrogen. It's about a 1 megawatt sized engine, which is commercially available and has been sold to various customers around the globe. And we are now rolling out that for the other engines as well. The next one will be the Type 6 by 2025. So that would be approximately a 3 megawatt platform for 100% hydrogen. And then the other engine models will come as well as demand is there. But we have basically a commitment that starting in 2025, we'll roll out this 100% hydrogen option for the other engines. And eventually we'll have a complete portfolio of engines which can run on natural gas and or hydrogen. And that's important, that these engines will have that dual fuel flexibility, which would allow customers to choose times when they may run on one or the other fuel or a blend. So having that flexibility is very important for our customers. And really any engine you buy today can be, when it is released, converted to 100% hydrogen. That is our commitment. And then we're pretty excited to see more and more hydrogen projects come up, and we're going to be ready for it. So with that, I think that was my last slide. I want to thank everyone, and we're going to now start the question and answer session. Thank you.
Hi, everyone. We have now reached the Q&A portion of this webinar. Before we begin, I would like to remind you that you can still submit questions via the question widget. Also, should you need to reference this presentation in the future, we do offer an on-demand version. The on-demand version will be available on the Business Review website. Now I would like to begin the Q&A, which will be answered by Karsten Strick, General Manager of Jenbacher North America. The first question starts, you mentioned that your cycle time is less than 12 months. What is the average?
Yes, thank you, Sabrina. Interesting question. And well, thank you and for listening to this webinar or seeing this webinar and participating in it. Coming back to the question, I would say the length of the cycle is close to 12 months, even in nowadays delivery crunches and scenarios. But we just completed the delivery of a 624 plant where we delivered the modules within 40 weeks, landed on site. And then we took another 5 to 6 weeks to install and commission it, as Christian alluded to. So basically that's the cycle time, so roughly 11 to 12 months. But of course, there might be different scenarios where we have longer delivery times. It's largely dependent on the number of engines which the plant consists of. Thank you.
Thank you, Karsten. The next question is, what variables affect the length of the cycle time?
Yeah, okay. I just alluded to that a little bit. It's the effects what we see is, well, within our control, it's the number of engines. Of course, we have production capacities, although we can probably deliver around 5 of the 4 to 5 large engines within every week, X works, but then they need to be packaged. They're normally being packaged. The large engines are being packaged in Austria or in Europe, then have to be sent over. That's on our side. On the other side, we're seeing a lot of times delays during the site construction, that permits have been late or have been delayed by the authorities. So we cannot build right away, or we cannot support the installation of the engines. And then the interconnect permit might be delayed as well from a certain point in time. But this is where we see the delays normally. And it's not only in the US or North America, we see that worldwide. These are normally the variables which affect the cycle time.
Thank you. The next question is combined cycle an available option?
If you're referring to combined cycle as installing an additional steam bottoming cycle, which delivers roughly 10% additional power of the plant, Jenbacher does not offer this as a standard solution, and we've looked into it, but it doesn't make sense in our power plant size. This is more a medium speed game or play, where on a 100 megawatt or 200 megawatt plant with 5 or 8 engines, you can get another 10% out of it, which is basically only with capital expenditure without additional fuel cost. But Jenbacher doesn't offer this right now. But we're going to look into it, whether it makes sense, because there is one thing with reciprocating engines where you cannot do a collective emissions or escape. So you have to have an individual exhaust gas heat exchanger on every engine, which then produce steam and go to one turbine. So I guess it's a lot of capital expenditure for relatively small yield.
Thank you. The next question states, any exhaust heat recovery option configuration for this modular type of power plant?
Yes, we do this modular power plants in all shapes and sizes. We can do it with a CHP option, meaning exhaust heat recovery, hot water, we can use as well. Yes, these options are available, and we normally customize the design according to what the customer expects and needs. An important aspect of the CHP is also when you design and build the CHP plant, this is currently incentivized by the Inflation Reduction Act, where you get an investment tax credit of 40 to 50% currently. Based on natural gas, and there is a time limit to this. I believe the time limit is end of 2025.
Thank you. The next question states, what is the maximum amount of H2 that can be injected with natural gas? What is the electrical efficiency and what is the electrical output?
Yeah. Well, there's no easy answer to that, but I think Christian alluded to this in his last slide, is we can blend hydrogen nowadays already into natural gas, and we also have 100% H2 solution. Currently, when you mix 25% of the hydrogen to natural gas, we don't have any derating, so the nominal load of the engine is the load you will get with the stated efficiency, so something between depending on the engine type, between 39 and 44%. When we go to 100% hydrogen, of course, there is a derating compared to natural gas because simply hydrogen is more explosive. It's harder to control. So where we are at now is on the type 4, instead of the 1.5 megawatt, which is the nominal load on natural gas, we are now at 1.1 megawatts. But I don't think that is the end of it. The more comfortable and more operational experience we get, and we have sold, I believe, 8 engines of these, which are capable of running 100% hydrogen worldwide currently, the more comfortable we get while we gain operational experience, the more prepared we are to increase the power to this for that type of application. The challenge we see on the hydrogen side, of course, is not that we cannot run it. The technology is there. We've done that since decades, I believe, with blended gases where we have a high content of hydrogen, 50, 60, 70% sometimes. The issue is more the current availability of hydrogen. Is there enough there to be able to run a power plant on 100% hydrogen over time?
Thank you. The next question states, how is Jenbacher improving or reducing the time for the critical spare parts as tech valves, cylinder heads, and others?
Well, a couple of approaches to that. Of course, the easy question is to keep more stock and to produce more of these and to have diversified stock around the globe. One of these things is we are increasing our stock and spare part stocks in the US considerably over the years, so we can deliver faster these components. And this is, well, it's work in progress and it's continuous because with the still supplier crunch over the last couple of years since COVID, let's say it, there might be also other components. So we're continuously monitoring this, seeing which components get longer delivery times, and then we adjust accordingly, order more stock, produce more, and stock it around the globe. So we have better availability.
Okay, thank you. The next question states, where can we find the information about the minimum space, the distance between containers? If one of our customers asks about the multiple unit operations, where can we find the information to tell the customer?
Well, I would say, I mean, I have a large application engineering team here in Houston, sitting in Houston or here in the US. I would say the first option should be to call us and we can help you in the design. We also offer extended scope of supply and we help you designing the specific power plant and trying to find ways of how to reduce space in between the modules, how to optimize everything. So I would say a quick call to us and sharing the intended layout and looking at ways of optimizing it should be your first choice.
Thank you. The next question states, what is power loss converting from CH4 to H2?
Well, as I said, the power loss, currently we are between whatever it is, at 1.5 megawatts CH4, the 420 convert, and if we run on 100% hydrogen, we are at 1.1, but we can gladly share the rating curve with you depending on the ratio of H2 mixed into the natural gas or vice versa. I would gladly share that with you. Mm-hmm.
Thank you. The next question states, really insightful presentation. Have you all considered doing modular biodigester units as well?
We as Jenbach, we are engine builders, genset builders. We specialize on power generation. Of course, we liaise with partners on the biodigester side, but it would never be, we would not focus on building biodigesters. I mean, there's probably much better companies there in the world which are able to do this. But we liaise with them and we partner up with them and trying to optimize the system if the client so desires.
Thank you. The next question states, renewable energy technology cannot compete with fossil fuel energy in terms of quantity and quality, reliability, and cost to the moment. Apart from that, renewable energy resources mismatch the consumption time zone where the major consumption of electricity comes in the night. Renewable energy resources produce electricity in the daytime, what is called duck curve problem. What is your vision to overcome the above 5 problems?
Yeah, thank you for raising that question. As a matter of fact, I consider this is the most important question of all in regards to renewable energy versus thermal energy with conventional or fossil fuels. It's not 100% true that, at least to my knowledge, that renewable energy is not competitive. You just have to take the downside of it and realize that, well, at the night the sun doesn't shine, as you well said it already, and there might be also calm periods where the wind doesn't blow, but that doesn't mean renewable energy cannot generate during the night, where you have the largest peaks in the early, late afternoon. But what we're doing is as follows. First of all, you've seen in our presentation that we're considering to run on renewable gases, and most of our engines which we sold in the past run on renewable gases, be that landfill, wastewater treatment gases, biogas. That's a given. Then we've changed to adapting our product portfolio to H2, which we can do to 100% with one engine type, and the others are going to follow starting 2025, and they're retrofittable in the future. In parallel, we are developing, or we have developed, our microgrid controller where we can integrate all these technologies, be that batteries, battery energy storage systems, solar, wind, coupled with our firm backup power, and to optimize the plant operation, seeing this as a whole plant or as a microgrid, and thus minimizing the use of fossil fuel or the use of renewable fuel. So this would be our strategy. We will never, to be specific, we would not consider manufacturing solar panels or wind panels, but what we can do is, with our experience and our technology, is to better integrate these systems so that we can optimize the renewable yield versus the thermal need and versus reliability. Because I still think, or I think we all think the same, the most expensive power is the power you don't have. But it's a topic, we're looking into this, we're looking into renewable gases, we're running on hydrogen already, and we're trying to integrate existing technologies, including batteries, or energy storage systems, solar, and intermittent renewable power plants.
Thank you, Karsten. Next question states, what are the financial benefits? How does this fit into the IRA tax credit?
Well, I mean, I alluded to that in the beginning, is the IRA currently incentivizes CHP installations based on natural gas. It incentivizes as well power generation, firm power generation, thermal power generation, if you use renewable fuels. So that's that we all can do, and I think that's the benefit where you can get a 40 to 50% investment tax credit with all the little fine print there is to the IRA and how to get this money back. And the second thing is, we've seen in a comparison now in this power plant where we compared reciprocating engines, our engine portfolio with gas turbines, for example, is we are cheaper on the CapEx side and definitely better on the OpEx side as compared to gas turbines. And I think that's an important factor as well. Our plants cost less than other technologies, for example. So there are these two benefits in there. And of course, the IRA is a big incentivizer in terms of CHP and renewable gases.
Thank you. Next question states, have you considered ammonia as fuel?
We're considering several fuels. Christian, for example, is part of a working group where we're looking into methanol, where we're looking into ammonia, where we're looking into storage of hydrogen. So we're looking at all types of fuel, gasifying then, of course, the methanol before it enters the engine. So there's large R&D endeavors looking into alternative fuels as well.
Thank you, Karsten. This will conclude our Q&A session for this webinar. If you have any additional questions, please feel free to reach out via email to Christian or either Karsten himself. Emails are listed on the presentation. There are also downloadable case studies in the download widget. So please feel free to download and read over any case studies that Christian went over during his presentation. Thank you all. Have a great day.
Thank you for listening and see you in the next webinar, hopefully. Thank you.